To program an industrial robot on the factory floor, you have to completely halt the production line. The machine must be taken offline, manually jogged into position, and taught its specific movements point by point. While the arm is stationary, the surrounding workflow stops. Every hour an engineer spends coding on a physical teach pendant translates directly into lost throughput, burning capital just to prepare the hardware for work. To scale operations without losing revenue to downtime, the programming phase must be separated from the physical hardware. This is the logic behind offline programming. RoboDK facilitates this by relocating the entire workflow, programming, testing, and optimization, out of the physical factory and into a strictly controlled digital space. Decoupling the code creation from the physical machinery allows engineers to develop new production cycles while the existing line continues to operate at full capacity. Moving to a digital space exposes a second major bottleneck. The industrial robotics market is highly fragmented, with brands like ABB, KUKA, and FANUC each relying on proprietary programming languages. RoboDK is a universal abstraction layer. A central software hub connects to distinct robot controllers, allowing engineers to validate complex sequences without writing manufacturer-specific syntax. As a digital twin, mathematical models guarantee toolpaths are collision-free before deployment. To see how this architecture operates, we will trace the precise pipeline from importing raw geometric data to hardware-native execution. The software functions as a rigid, physics-aware validation engine that pre-solves mechanical interference. The workflow begins with an empty, spatially defined 3D coordinate system. Engineers import the native 3D CAD files into this grid. The physical components, the workpiece, the fixtures holding it, and the end-of-arm tooling are loaded into the coordinate system. The precision of this geometry dictates the validity of the simulation. If a virtual fixture is off by even a millimeter, the resulting program could cause a physical crash. Once the spatial environment is set, the correct physical robot is introduced from the software's internal library. Selecting a specific model automatically loads the exact mechanical parameters defined by the manufacturer. These represent the kinematic constraints. The software immediately calculates the physical reach, the joint rotation limits, and the unique movement capabilities of that specific robotic arm. Binding the exact geometry of the workpiece to the rigid kinematic rules of the hardware transforms the static 3D model into an accurate digital twin. Manually teaching a robot to trace a complex curve by jogging it from point to point is slow and prone to human error. Automated path generation resolves this. Rather than guessing coordinates, RoboDK extracts toolpaths directly from the geometric data of the CAD file. A continuous path is mapped perfectly along a complex curved edge or surface. With the path generated, the digital twin runs a full simulation, testing the planned movement against the mechanical limits of its joints. This triggers the active collision detection engine. If the software detects any spatial overlap between the tool, the robot, and the fixture, it instantly flags the mechanical interference. The engineer manipulates the virtual path to clear the obstacle. The route updates, finding a safe trajectory without putting physical equipment at risk. This spatial awareness is especially critical when scaling up to multi-robot cells. Operating multiple robotic arms within the same footprint requires extreme spatial synchronization. The arms must weave around each other and the workpiece at high speeds. RoboDK manages these overlapping workspaces, ensuring the timing and positioning of both machines remain synchronized to prevent impacts. Validating the physical space is only the first step. The system must also validate time. Because the software knows the precise kinematic profile and speed limits of the robot, it calculates exact operational cycle times based on the validated path. This cycle time estimation allows plant managers to integrate the robotic cell into factory production schedules and optimize resource allocation. Running these virtual trial and error cycles eliminates the risk of hardware damage while replacing scheduling guesswork with mathematical certainty. A digital simulation is only useful if it translates to physical action. How does this spatial data become machine movement? A physical robot controller cannot natively read raw 3D geometry or generalized splines. It requires its own specific dialect of code. This translation is handled by the post-processor. The post-processor takes the universal spatial data and compiles it. The visual 3D path enters the processor and is converted into a structured array of executable commands. It automatically maps the generalized movements into the proprietary language required by the target controller, such as KRL for KUKA or RAPID for an ABB system. This translation happens seamlessly, requiring no manual coding or syntax knowledge from the engineer. By abstracting the programming complexity away, the workflow remains focused on the manufacturing outcome. The final deployment step is transferring this compiled, native file directly to the physical robot controller on the factory floor. Built upon precise kinematics and tested against strict spatial rules, the physical robot executes the program exactly as it was validated in the simulation. The post-processor bridges the gap, translating the theoretical perfection of the digital twin into the practical reality of the factory floor. This pipeline, transitioning from a static CAD file to an optimized, natively coded robotic program, can be executed with zero production downtime. This offline programming architecture is highly versatile, deploying across different industrial sectors. It allows machinists to optimize complex CNC toolpaths and ensures absolute geometric consistency in automated robotic welding. The same underlying architecture scales to program intricate additive 3D printing tasks or to automate complex spatial logic for palletizing. As industrial automation scales, this software architecture will continue to evolve. We are already seeing the integration of robotics into broader Industry 4.0 frameworks, creating smarter, highly connected manufacturing environments. Artificial intelligence will eventually assist in the programming phase, autonomously designing and optimizing path plans based on learned efficiencies. Simultaneously, the shift toward cloud robotics will allow plant managers to coordinate multi-factory systems from a single, centralized digital twin. As collaborative robots gain traction, pre-validated simulations become even more critical. They guarantee safety when machines operate immediately alongside human workers. RoboDK's core value lies in its ability to maximize operational efficiency, guarantee physical precision, and eliminate the financial drain of machine downtime. Offline programming and the digital twin serve as the primary command centers for modern agile manufacturing.